Okay, so it's chapter 7, internal forces, and we are doing the shearing force diagram and bonding moment diagram. So first steps, remember, find the reaction force. Okay, so we have a pin connection at this first point, and let's call this AX and AY, and we have a normal force at B and B. Okay. Oops. For this problem, because it's a distributed load, we need to find the reaction force petit a, first little a. We need to find the resultant force first, right? And its location, resultant force and its location. So resultant force for a triangle, it's equal to, so FR, it's equal to the base 6 times the length 9 and divided by 2. So it's 3 times 9 is 27 kilonewton. And for the location, okay, it's 2/3 from the top of the triangles or 1/3 from the base. So this distance there is 2/3 times 9, that is equal to 6, or 1/3 times 9, that is equal to 3, and it's meter. Okay, so now that we have the reaction force, make it bigger so we can see it, we can find the NB, the AX, and the AY. Okay, so find the reaction force, resultant force, locations, and now we can use the equation of equilibrium, right? So sum of the forces on X is equal to 0, give us AX is equal to 0. Bam. And now we need to use a moment. Let's do the moment about A. So sum of the moment about A is equal to 0. So we have the resultant force FR that's going in the negative directions times the distance of 6. And we have NB going in the positive direction, so plus NB times the total distance, that is 9. It's equal to 0. So NB is equal to FR. How much is FR? 27 times 6 divided by 9. So NB it's equal to, I don't have my calculator, I can't find it. How much is that? It's 18 kilonewton. It's 2/3 of 27, yes. And if we do sum of the force on the Y, it's equal to 0. We have AY minus 27 plus NB, it's equal to 0. So AY it's equal to 27 minus 18. So AY it's equal to 9 kilonewton. Okay, so we found NB, AY, and AX. Okay, so now we can draw. So we find the resultant force, but we just find the resultant force because we needed to find the reaction force. Okay, now the second step is to cut the beam and keep, let's say we will keep the left side. Okay, so what we have now, it's a beam that is shorter than 9 meters. It's the length is x, okay, any x, and we have a load on top of it, triangle load. Okay, this distance is x, so this distance is x. How much is that? Okay, how much is that? So this one is 6, the total, this one is 6, but, and this one is, if you write the little f(x), the distributed load, the function of the distributed load is going from 0 to 6 in 9 meters. So it's equal to delta y divided by delta x. So delta y, the delta y is 6, divided by the delta x, that is 9, times x. So it's equal to 2/3 times x. Okay, so it means that if for x equals 0, the distributed load is equal to 0. For x equal, for example, 3, so here the load is equal to 2. For x it's equal to 6, there the load is equal to 4, and for x it's equal to 9. 9 divided by 3, 3 times 2, 6. We find the 6 there. Okay, so the function of this curve, the function f of x, it's equal to 2/3 of x, right? So this 8 there, it's equal to 2/3 of x. Yes, and this distance there is x, right? So the resultant force of this force, so the resultant force, it's equal to Fr at x, it's equal to 2/3 times x, that is the base, times the length, that is x, divided by 2. So it's equal to 1/3 of x squared. Okay, this is the resultant force. So we can replace, that was the beam. Okay, so we can replace, that was the distributed load, right? Like this. We can replace the distributed load by, are you still there? We can replace the distributed load by one resultant force, Frx, that is equal to 1/3 of x squared. And the location is 2/3 of x, like this. Okay. And we should not forget that we have the Ay, and the Ay we found that is equal to 9 kilonewton. 9 kilonewton. So that's our little, that's our left side of the beam. We cut anywhere, okay, anywhere between 0 and 9, and that's our resultant force. And now what we want to find is the shearing force at x and the bending moment mx. Okay, so we will use this free body diagram to solve for Vx and Mx. And this distance there, let me put it in, is 1/3 of x. Okay, the total length of the beam is x. This is 0, and this is x. Okay, so let's do some of the forces on x. It's equal to 0 for this one. So we have a y plus minus the f r x and minus v of x is equal to 0. So we have v of x that is equal to ay that is equal to 9 minus 1/3 of x square. That's the function for Vx, and it's kilonewton. And some of the moment about, let's do the point x, it's equal to 0. So if we did a mistake to Vx, we don't reproduce the mistake for the moment at the point x. Sum of the moment at the point x. So we are looking to find the function of the bending moment, and we will use the moment about the point x. It's equal to 0. Okay, so yes, I should not, sorry, like this. So ay is rotating in the negative direction, so minus ay times the total distance between ay and Vx, that is x. And Frx is rotating in the positive direction, so plus the Frx times the distance, that is 1/3 of x. and this mx is rotating in the plus direction. So plus m of x is equal to 0. So m of x is equal to the plus ay, so 9 times x minus for the FRX, so 1 minus 1/3 of x squared, because I switch it to the other side, okay, time 1/3 of x. So m of x is equal to 9 times x minus 1 divided by 9x cubed. Oh, what's happened? Oops, that was weird. Anyway, and let me square that. So we have v of x in kilonewton, n of x is kilonewton time meter. Okay, and that's just one function for the entire beam from 0 to 9 meter, because we find the function that describe anywhere from 0 to 9. Okay, it's not two functions, it's just one function. There is no step, no gap in the load, like the load is constant, increase slowly. It's not like ups, we have a force, we have a moment. Okay, that's why we can use only one function. So now we need to draw that. Okay, so let's draw that. Shearing force, so that's V of x from 0 to 9, and that's the moment m of x from 0 to 9. For x equals 0, v of x is equal to 9. So for v of 0, it's equal to 9. And for v of 9, it's equal to 9 minus 1/3 times 9 square. So v of 9, it's equal to, how much is that? Oops, minus 18. Okay, so it goes up to like there, minus 18. What you can find is where it's equal to 0. So where is it crossing the axis, the x-axis? So for that, you need to take the derivation v prime of x. That is equal to 1 minus 1/3 times 2x. So it's equal to minus 2/3 of x. No, you should not do that. You should solve, sorry, for v of x is equal to 0. So 9 minus 1/3 of x squared is equal to 0. So 1/3 of x squared is equal to 9. So x squared is equal to 27. So x is equal to the square root of 27. And this is equal to 9.20. So this is 9.20. That's calculus questions, right? Okay, and what you can do also is take your calculator and draw the curve. It's look like this. Oops. Okay, something like that. That's a bit more steep there. Oops. Something like that. Oops. So your shearing force is positive between 0, x equals 0 to 5.20, and negative between 5.20 to 9, and it's going to minus 18. And remember that your curve, that your load look like this. Remember? We cannot really guess that the shearing force will be so different than the initial loading force. Let me do it better. And we have a 9 and we have the 18. Remember? So that's this 9, and that is 18. So we are sure that we find the right function if when we solve for V9 we find minus 18, we should find this one. And it must come back to 0 and to 0 and begin to 0. So that's for the shearing force. So let me write that the shearing force, that was the load, the distributed load, and now let's do the moment. That's this equation. So what we can see, if we do the moment about 0, what is that? If we replace x by 0, we find 0. The moment at 9, how much do we find? So it's 9 times 9 minus 1 divided by 9 times 9 cube. So it's equal to 9 square minus 9 square. So it's equal to 0. Okay. The maximum will be, so m is max when v is equal to 0, because v is the derivation of the moment. Okay, so move that's for the next question. So here your moment will be maximum. Okay, it begins to 0, it stops at 0. It's maximum when v is positive, v increase, and when v is negative, the moment decrease. Okay, and it should look like something like this. Here we go. And your moment doesn't have any gap, any step, because we don't apply any external moment on the structure, only a load. So the moment is smooth. You see this curve is smooth. To have a gap in the moment, like something like, for example, like this, we need to apply an external moment. And we can find the maximum value of the moment. So this is the same as this one, of equals 0, so the 5.20. So we need to solve for m of 5.20. So replace x by 5.20. So 5 times 5.20 minus 1 divided by 9 times 5.20 cube. And this is equal to 31.2. So this value there is 31.2. So you see the maximum bending moment, it's not exactly in the middle. It's at when x equals 5.20. So that's could explain. It's not the same load, I know. Oh no, we should not do this. If the load is like this, we should increase the thickness of the beam at 5.20. Okay, so that was the graph of the bending moment. Here we go. So we solved for the graph. So remember what we did. Oops, that's a long step. We find the resultant. So we have the initial distributed load. We find the reaction force to find the reaction there at AY and NB. Okay, so that's this one and this one there. After that, we cut the beam. We keep the left side, and we need to reduce the distributed loads only on this portion, on this side of the beam. And after that, we need to solve for the internal load, and using the equation of equilibrium, we find the function of the shearing force and the function of the bending moment. With those functions, we can draw the graph. So take your time, and I just asked you a question in the online quiz on the previous example and this one. The next problem I will do is just a little bonus problem to explain you what's happened when we introduce a moment, a couple, somewhere in the beam. So that's it. Bye-bye.